Okay, so officially then, happy garbage day. Woo! Happy I walked to work without a coat on day for the first time this year. That's exciting.
You must be relatively close.
No, like from my car.
Oh.
Yeah. I walked to work from my car, from the parking lot. That was exciting. Let's see, a couple housekeeping things here. Tomorrow, my office hours need to be cut short at 3:30. I was asked to go to a campus-wide meeting, and so I said I would go and do that since I figured at this point, homework was going to be due Monday when I agreed to that, but now it's due Friday. But Vladimir, have you gotten a lot of questions on homework too?
No, the main thing has been the discussion about the differences in the slopes across submodels for section 3.
Okay, differences
But-
across slopes.
Yes, so my advice is just pay attention to the sign of the coefficients and then read the instructions twice. After doing that, you'll be fine.
Yes, so the first submodel should be the -1 in the comparison, and the second one would be the 1. So it follows my example pretty carefully. And yes, reading instructions is always a good pro tip.
Twice is even better.
Twice is even better, indeed.
Mm-hmm.
So that's due Friday. I put up new materials for today, so please grab those, and if you haven't already grabbed them. And then next week is break, so no office hours, no classes. After break, you have a bridge activity, and I've already gotten a couple questions about that from some folks who've been working on it, so I wanted to explain a little bit about it. So this is another sort of half and half. The first half is reinforcing the idea of interactions and especially coding for getting simple slopes out of that. And the second half is focusing on count models. So you should be able to do the first half right now if you felt like it, and the other half after the end of this week. But I wanted to just describe the idea here. So does this equation look familiar? You had a formative assessment where this was the equation, and half of you couldn't see it for some reason. Still haven't figured that out, but I've typed it in here this time, so it should render without problem. So I asked you a bunch of questions about this equation, like what would be the predicted f-slope for somebody with a g of 2, like those kinds of questions, and we went over them. Well, now I'm asking you to identify which code would give you the correct answers for these things. Because in homework 3, you will end up with interaction terms where I ask about simple slopes. This is a chance to keep practicing on this idea. And so in Stata, let me blow this up. I can blow it up only a little bit more, just a little bit more. So Stata is Lincom and R is sites GLHT. So you can choose to ignore one or the other of these lines based on which program you're trying to specialize in. The R1, these are multipliers. So for instance, this is asking, what is a predicted Y outcome for somebody with these values of the predictors? So the values in here would be multipliers, what would go into the equation in the spots of the parentheses here. In Stata, the values are the same as what's on the end of these variables. And in Stata, when you type the name of a variable like f, you're not talking about f the variable. You are talking about the slope of f as estimated by the model. So f means beta 1, g means beta 2, and so on. But the numbers should match across. And in talking about this, I realized that Stata does not use stars. It uses hashtags or pound signs. So I need to go through and change all of those, which will be laborious, unfortunately, but it shouldn't affect the outcome. So only one of these is correct. I'm asking for you to figure out which one. And the others that are incorrect in deliberately specified ways based on common patterns of errors that I've seen when folks are learning how to do this. So we're going to go over it, right, Vladimir?
Yes.
He's going to go over it with us on the Monday after break. So let us know if you don't understand or if you want to talk through like why the answers are right kind of thing as you're working through this. We can do that. Yes?
Will you be able to get through the second half by Friday or
Yes.
through Thursday? Okay.
Yes, for sure.
Okay.
Yeah, because there's no more class next week, so that wouldn't be fair. So we're going to start talking about concepts in predicting counts, links, distributions, and scales. So very similar to what we did in the last one for binary. So any questions or comments on that? All right, so then we have, let's see here. Where is that? I didn't put it up. I thought I put it up.
You're looking at 4. Go up.
About 3?
3.
No, I was looking for the homework plan. I put that up, I thought, but then it got un-upped. I think what happened is I had my page and then it got written over at some point. I had put up homework 4's plan for you as well, and now it's not here. So after class, I will do that.
Thank you.
I had intended for that to be there. So I try to make things due much in advance, but that will be
Would you
due the
like an
following Monday.
email? I can do that if you would like.
Send me an email to remind me?
Yes.
Yes, please. Yes, my email, for better or worse, is like my task list. So
I understand.
if
That's
there's
why.
not an email for it, it doesn't exist.
Understood.
Thank you. Yeah, I intended to put it up, but that way you can complete that and submit it via Icon. And it should not take very long. I'm just making sure that folks are able to identify a data set and some variables. And I have in the plan document a whole list of places that have public access data, and I found a couple more that I added to that for this year. So those are the things that are on tap. Let's see, the week after break also, we are being kicked out of our classroom one more time for comprehensive exams. So we'll be on Zoom the Thursday of that week. All right, anything I'm forgetting or you want to ask about? Housekeeping question?
Just for clarity, homework 4, are you referring to any difference between homework 4 and 5?
Hope 4 is the only one that where I'm asking you to find a data set and run some generalized models on it. So it's an individual writing assignment.
Okay.
5 is going to be due at the end of finals week, and that is going to be another online version. It's actually going to be a path model.
Okay.
So 2 separate things. So the idea of the plan document is that it's essentially an outline that I want you to complete. I will read it and try to weigh in and to guide you on what would be most useful for you to help answer your questions, and then you will execute said plan. So I think we talked about this last time. I will give you a rubric as to what I'm expecting. And things like, if you're doing this kind of model, here's what you should be reporting. If you do this kind of model, here's what you should be reporting. It's not a paper. It's like the core of the inside of a paper. So research questions, a little bit of a method section, results are the main thing, and then a 1-paragraph discussion where you summarize what you found. So it should not be more complex or longer than any of the other homeworks, but hopefully it should be useful to you and get you started on something that could become something, a contribution in its own right. So that's the idea. So anything that we will have covered like by that point is fair game. So counts is what we're doing next. We're leaving the world of categorical for now. All right, are we ready?
Mm-hmm.
Counts.
One question.
Yes.
Do you recommend same or different data sets between 4 and 5?
So 5 is not an individual specific one. I'm going to give you data sets like usual. So 4 is the only one where you have to find data and plan something to do with it. And if you already have data that you're working on in your research, or if your advisor has a data set they want you to analyze, that would be a great choice.
Okay. So that's
Yep. And if you're doing some other project for some other class and you're like, can I double dip? Yes. Efficiency is good. Totally fine with that. All right, other questions? Okay, then away we go. So a first is a roadmap of where we've been and where we're going. So generalized, when you hear that word, what do you think? What's this class about?
Beyond the linear model.
Continue-ish.
Continue-ish, yeah, beyond continue-ish. So linear models as standard linear regression, for instance, general linear models are predicting what outcomes that are supposed to be conditionally normal. So ised means some kind of not normal. And because it's not normal, because it's not continuous rather, we need link functions as well to keep our predicted outcomes within the scale they should possibly be. So that's the family of generalized models extends traditional regression to predict other kinds of outcomes. That's the idea. So I have in purple here, I'm not sure how, yeah, you can kind of see it, link function and then other conditional distribution as the pieces that you would select for different kinds of outcomes. So what we just did in Unit 2 is categorical, meaning binary, ordinal, or nominal. So the links that we would have used for that, good job Zoomers, logit, probit, log-log, or complementary log-log were the ones that I had shown you. Remember what a logit is?
The log of the odds of the
Probability of a 1. What's a probit? Something with a z-score, that is correct. Yeah, it's the z-score that goes with the probability as the area to the left of a standard normal distribution. So it's the same idea of making something that's truly continuous, but just in a different metric. A log and complementary log, I don't even have these memorized. They're asymmetric link functions. One is for data in which 0 is more common, and one is for data in which 1 is more common. They're much less often used, but I wanted you to be aware of them. In terms of what the distribution would be, it was Bernoulli for binary, which means there's only two choices, and then multinomial is what it would be for ordinal or nominal. So categorical data are not distinguished in terms of their distribution, they're distinguished in terms of their link functions. So we talked about different links for ordinal than for nominal, right?
Mm-hmm.
Ordinal is the one where it's like 0, 1, 2 versus 3, 4, 5, and then 0, 1, 2, 3 versus 4, 5, and that kind of thing. Nominal is one of the outcome categories is the reference, and each of the submodels tells you the probability relative to the other choices. So we did that. Now, where we are, counts. Good news, link function is log, the end. There's another one, inverse something or other, that breaks my brain and I've never seen it used in practice, so we're just gonna pretend like that doesn't exist. It's fine. The tricky part, I have here words that are hinting, foreshadowing, some kind of, meaning there's gonna be choices. So the new concept for this unit is we have decisions to make about what the most appropriate distribution should be. For counts, you're gonna see 4, maybe 5 or 6 potentially. There's a lot of them. So that's where the some kind of comes. The 5 or 6 potentially is if we incorporate what is known as zero inflation, which is a count variable that has a big pile of zeros because you have 2 different subpopulations. A population for whom the count is not relevant and a population for whom it is. So we'll see models for that. And yes, this is the word hurdle. Like the thing you jump over and track, that's what the model is called. So, shout out to my niece Amelia, pro hurdler in Omaha. Woo. Track season just started for high school kids. Her parents stream her races so I can watch them later, which is really cool.
Long or short?
Sprinter. Yeah. She's a hurdler. So the longest they do is 400 meters or 300 in certain states.
Okay.
That's a long way to go, though,
It is.
when you got to jump. Anywho, later, coming up next, the next unit is things that are not normal but sort of catch-all, like potpourri. So proportions, truncated or bounded data, and then skewed continuous. So other kinds of not normal in Unit 4. And then we switch gears to multivariate.
Mm-hmm.
So a taxonomy also, in terms of how to classify not normal outcomes, is discrete versus continuous. Up to this point, we've been in discrete land. So all responses are whole numbers, integers. Categorical variables are in which the values are not numbers, they're labels. So you can predict the probability of a 1 or a 2 or a 3, but those are just labels for answer choices. They're not numeric values. So in that case, we would pick a distribution of Bernoulli if I only have 2 choices, or multinomial if I have 3, and then the question is which link function. Our choice of link then dictates whether we're thinking about it as ordinal or nominal. What we're doing now is a count of things that happened. It's still considered discrete. So how many cigarettes have you smoked today? How many days did you stay in the hospital? How many times have you done this? These kinds of things. In research context, you might see something like amount of disruptive behaviors, something like that. How many times you hit your little brother today? That kind of thing. How many times I have to say, I just said that to my son before he does something. What did I just say? That's a count distribution, highly skewed sometimes. So it ranges from 0 to positive infinity. So logits aren't going to work for this. Logits are for outcomes that are bounded in up and above and below, or bounded only below. So our friend log is going to solve that problem. And then some kind of distribution, we'll figure out more about how to choose amongst those. Our main concern is keeping predicted outcomes above 0, because you can't have a negative count. Then the question we have to figure out, though, is what distribution fits, and what do we do if we have extra zeros? The other kind of outcome then would be things that are truly continuous, where responses can be any number, not just integers. So things like heart rate, income, like money, anything related to where you have blood pressure, anything that's measured very continuously, only limited by the amount of measurement, that frequency of measurement. And we'll have the same question about what kind of distribution we should use for this as well. So here, terminology. Our link function for count outcomes is going to be the log, natural log. You already learned this. There are 3 different scales that you need to be aware of, just like there was for binary data. So we had the original data for binary that was zeros and ones. Then we talked about the scale of the conditional mean that's being predicted by the model as the probability of a 1, and that was continuous between 0 and 1. And then we took that probability and converted it into odds and converted that into logits, right? So we have all these different scales operating. Same idea is here. We have our original count as the column in your data set. That would have like zeros, ones, twos, threes, whatever your count is. What is being predicted by the model is the expected count. So this is analogous to probability for binary data. So I'm predicting like the mean of a count variable is the expected count. It's on a scale that's continuous because you can have like the mean of a count variable be 3.2, but each of the counts is discrete integers. To keep the expected count positive, that's where the log comes in. So the log of the expected count is what the model is going to predict directly. And you will hear me shortcut this to say log count, because log of the expected count is a mouthful, but that's really what it is. So then to get it back into the scale of expected count, we exponentiate. So e to the predicted log count gets us back into expected counts on that metric. And what's going to happen is that when I put in a slope predicting log count, the slope can have a linear relationship because log count goes on forever. It's unbounded and it ranges from positive to negative infinity. But when I unlog the predicted outcomes, exponentiate them, then we get slopes that look like this. So a positive slope asymptotes as it gets towards 0 and shuts off, but it doesn't need to asymptote the other way. So it's like the half of the logistic curve that we saw before, just the bottom half. And the same thing is true of a negative slope. It has a vertical asymptote and it shuts off as you go away. So log is the new link function. That's what I want you to know. So the link then, log, inverse link is exponentiation. So the notation that I'm using for this is different than what's in the book, but I have reasons. I'm using mu to describe what the model predicts directly. And then so e of y, the expected count, would be e to that. So putting some numbers on this. So let's say that my model told me my predicted log of the expected count was -1. That's okay, because log counts go on forever and ever. But you're like, what's a log count? That's another unintuitive metric, just like logits is. So if we unlog it, exponentiate it, that works out to be an expected count of 0.368. So this is like saying the mean of the counts. If you had a count data that had heavily skewed towards 0, you might have a mean that's small. So expected counts are not integers, but real counts are. Just like we had zeros and ones for real that we predicted as probabilities in the model. So that will be one of the questions on your bridge activity, I will tell you that much. If you have different ranges of opportunity in which to observe counts, or you have different expectations just based on like how much is there in the first place, you might want to use an offset. So let me give you a couple examples. If you are counting how many disruptive behaviors a child engages in, you need to know whether you were watching them for 5 minutes, 10 minutes, or an hour. Because theoretically, they'd have more chances to be disruptive the longer you watch them. Well, you might intend to watch all the kids in your study for 10 minutes. But one of them needs to go to the bathroom. And someone else was so disruptive that they got kicked out of class, and you can only watch them for 2 minutes, right? Things happen. So if you want to control for like exposure is the way that it's talked about, you can include something called an offset. And what that is a predictor that you would log transform so that's in the scale of the same model, and its slope is fixed to 1. That essentially turns a count into a rate. Another instance in which you might do this is looking at, let's say, proportion of people. I have an example I built for a different class. Proportion of people, number of people who get skin cancer. So one of the things you might want to control for is number of people who live in a region, period. Because places that have more people are going to have more cases of cancer. So if you want to think about things in terms of rates, an offset or an exposure can help you do that. If you want to think of things in terms of proportions, and that's easier for you to think about, that's the next unit. We're going to predict proportions as like accuracy or things like that. So this is not well explained in most places, but it is available as an option in most common software packages. The example I'm going to show you doesn't use this. It's just everyone has the same opportunity to show their counts. And guess what? Do you remember odds ratios? They're back, but they have a new name for no reason. These are incident rate ratios. And do you know how you get them?
Same way.
Same way, e to the slope. So e to the slope gives you an effect size called IRR instead, and it is scaled the same way. So values between 0 and 1 would indicate negative slopes. A value of 1 would indicate no relationship, and values above 1 indicate positive slopes. So here's some examples of how you might talk about this. If I have an IRR of 1.25 for the addition of a characteristic versus not having it, then I would say people who have it, their counts are 25% higher. If it's a negative relationship, I might say people who have this are 25% lower. So this is also something you can commonly ask for in software that I don't usually see reported. But if you want to provide effect sizes this way, you can. However, I'm going to show you how to build something that looks like an R-square because we're back to numbers again. Because I can build predicted counts, and I have the real ones, and I can correlate the two of those and square that correlation and get something that is a true R-square. So that's probably a more intuitive way to think about it. So we don't have to worry about what link function we're going to use. What we're going to end up having to worry about is what distribution we use instead. We have choices, and we have to evaluate the relative fit of these choices. Good news, you already know how to do this.
Maximum likelihoods.
Yeah, we're going to compare the likelihoods and see which one's taller. Same idea. Likelihood ratio test is what we'll use to do this. All right, picture time next. How are we doing so far, folks? So we're using logs to predict expected counts and keep them positive. We are not log transforming the data. We're log transforming the mean to be expected. Just like we didn't logit transform zeros and ones, we logit transformed the probability of getting a 1. So,
a lot of times when we talk about data that or at least I think about in a continuous way, it seems like a lot of those things are probably really technically counted.
counts are very common.
Yes, but a lot of things that, I think we kind of think about as continue-ish.
Yeah, that's my word.
Like how do we tell the difference? Like when is it continue-ish enough that we can use a linear model, and when do we need to switch over to a generalized model for count?
Great question. So let me repeat it for the recorders and the Zoomers. Counts are very common. At what point is it continue-ish enough to where we can say as normal is fine? Here's a picture that might help. So the orange line, does that look normal to you?
Yeah.
The purple one? It's kind of it has a little tail. What about the blue one?
A lot better.
Yeah, a lot better. So one common wisdom is after you move off of if the mean of the count is greater than 6 or 7-ish, a normal approximation may not be too bad. What I would be worried about though is predicted counts that go below 0. So if you wanted to treat your count as if it were sufficiently normal to use a standard model, I would watch for predicted counts that go outside boundaries, and if that happens, I would probably want to change it. So this is, anyone speak French in here?
Poisson?
Poisson. I don't speak French,
It's
but
not poison.
no, it's not poison. It may feel like poison, but it's not intended to be. I believe this means fish.
Yes. There actually, April 1st is Fish Day.
April 1st is Fish Day.
Sunday day of Vril.
Okay, I learned something new today. I don't know why this is called Poisson. I don't know if it's a person who made it or has something to do with fish.
I think it was a person.
A person seems the most likely explanation. Maybe the person was a fisherman. I don't know. But I don't need you to memorize any formulas, but they're here in case you want to see them. The main idea that I want you to know about this distribution is that it also doesn't have a separately estimated variance. The variance is determined by the mean, just like it was in Bernoulli and multinomial. And it's not only determined by the mean, it is the mean. So in other words, the orange line is describing a distribution that has a mean of 1 and a variance of 1. The purple line is describing a distribution with a mean of 4 and a variance of 4, and the blue one has a mean of 10 and a variance of 10. And the reason these are dots here is to describe the idea that this is not a continuous distribution. There is a probability of a 0, a probability of a 1, a probability of a 2, and so on. Vladimir tells me the Poisson distribution is named after French mathematician, I'm going to go with Simeon, S-I-M-E with an accent O-N.
Good enough.
I just know that in French you have to sort of trail off and not pronounce the end of the word a lot, like symbol. That's my French interpretation. So it's named after a person who may or may not have been a fisherman. Okay.
So when we're trying to figure out which one to use, it all depends on lambda, which is kind of like the mean, and also the variance.
It's one
But
parameter.
it doesn't depend on our sample size, and it doesn't depend on how many, count is in our range. It depends on what is the mean in the range. It has to be 7 or greater.
Yeah, so at this point, once you have something that looks reasonably symmetric, then a normal approximation is not going to be too bad. You don't have a lot of people who are zeros, and so you're not going to have a lot of predicted people below 0. Whereas if you try to fit a normal model for the orange one, you're going to have negative predicted counts because most of your data is right up against that boundary. So I would say it really boils down to how symmetrical your distribution looks and how likely you are to run into the boundaries. Unfortunately, though, there's not an easy way to compare distributions that have different definitions of height. So the normal formula has one definition of height. Poisson has a very different definition. It's right here. So you can't say, well, normal's taller, so that one wins. They're not on the same scale. It's like centimeters and inches or Fahrenheit and Celsius. But within the count family, those are more or less on the same scale because they're nested, and we'll see that in just a second. So this will be the first one. I have never once in my life seen this fit. Never. But this is the jumping off point, though.
Poisson never.
Never. Not once.
Is there a explainable reason for that, or just kind of a luck of the draw?
Because what often happens in count data is that you have this really long tail, and there's too much skewness, and that pulls the variance to want to be bigger than the mean. So skewness is not expected in most of the Poisson distributions the way that it is in the others. But this is the one that people start with because the others are, then we add stuff to this one to make it fit better. This is the base model. If you're buying a new car, right? The base model has a certain price, and then if you want, fancy speakers, then that's up this. If you want this, better leather, up this. It's like that. This is the base model. Nobody wants to buy it. So here's the 3 problems that Poisson runs into in practice. Number 1 is the most common, when the mean and the variance want to be different numbers. It can go either way. So these are some new vocabulary words. If the variance is less than the mean, that is called under dispersion. So dispersion means how spread out things are.
So
Yeah, it's squish. Yeah, highly, platy? Leptokurtotic, kind of like this one. If variance exceeds the mean, this is very, very common. This is over dispersion. So this is the one that we will need to fix most often. I'll show you how to do that in a couple different ways. Negative binomial is the one that we're going to focus on. When there are no 0 values is the second problem. So not all counts start at 0. And when I first saw this, I was like, well, I can fix that. I'm just going to subtract 1. Problem solved. Doesn't work. We need a different distribution that doesn't have zeros in it, is the answer. And number 3 is when there's too many zeros. Then we have to do something about it.
Is that the hurdle?
That's going to be that's one solution to it.
Well, I'm going to say it's not.
Yep, that's one solution. So problem number 1, variance exceeding the mean over dispersion. We have a new distribution called negative binomial. This one's ugly. Don't ask me to explain this probability density formula because I can't. Flat out can't. Here's the part that I can't explain though. This little thing right here. Negative binomial adds a parameter that I have denoted as k that you can think of as a stretchy factor. It pulls the variance apart from the mean. So the variance is then predicted to be whatever the mean said it was, plus the mean squared times the stretchy. So if k is unnecessary, if Poisson is sufficient, it would be estimated as 0. This part goes away, and you're left with Poisson. So negative binomial adds a stretchy factor that accounts for skewness. It's very common in software. Here's another one that you might also see. This is much less common. I just wanted to point it out there. Here's a picture that's going to help. I made this one too. I didn't even steal it from Wikipedia.
Ooh.
Aren't you proud of me?
I'm very proud.
I know. I made this a very long time ago to make sure I could understand what the heck I was talking about.
How many points did you use to create your?
A lot.
Approximately.
A lot. This is an Excel picture.
Oh, very good.
So the red line and the blue line. These both have a mean of 5. The difference is in what the variance is predicted to be. Blue line was generated by a Poisson distribution with variance of 5, no stretchy whatsoever. So you can see that it looks like this. Red was generated with the stretchy factor of 0.25, so it makes the variance into 11.25. So red has more skewness to it. It also, the mean is shorter because more of the distribution is pulled to the right. Likewise, green and purple both have a mean of 10, but purple has the stretchy factor. So count data often looks like the red and purple lines. So because k is something that we could take it or leave it, if we have k above 0, that changes it into this other function. We can do a likelihood ratio test to see whether adding k makes the data taller. The likelihoods are comparable. So if the height of the data, if the log likelihood increases by 3.84, or said alternatively, if the -2 log likelihood decreases by 3.84, then we keep it. Nested model comparison. One catch though, because k can't go negative, we actually should correct the p-value for this to account for that. So this is the idea of a mixture distribution. Essentially what we're going to do is cut the p-value in half because k is positive, and testing it against a null hypothesis of 0 doesn't make sense for a two-sided symmetric distribution. So that's something that statisticians care about. I put it in here because you may have to care about it at some point to make reviewer 3 happy, but I don't care about it as a general rule. I'll show you how to do it though in software. All right. Do you want to see some numbers?
One quick question.
Yeah, go ahead.
Does the software produce the k that may or may not be effective?
Yeah, it tells you what the estimate of it is,
Thank you. Yep.
and it gives you a hypothesis test for it. The only problem is in how k is represented across packages. So when I first built this unit, I was pulling my hair out because like in SAS Glimix, which is what I was using, k is labeled as a scale factor in the output. And I'm like, okay, that's fine. In Stata, it's labeled as alpha. And alpha is like 7 other things in statistics already.
It's everywhere.
And then in R, it's labeled as theta. So, and sometimes you end up with 1 over it in the output instead. And I think that's because of, in these here, most of the time it's 1 over k. So I'll show you how we can get those things to correspond. But this is where we were.
Yes, but number time.
Yeah, number time. Questions before we have numbers?
Do we need to know how to detect there's too many zeros in?
Do you need to know what? I'm sorry?
How to detect there's too many zeros in the data?
We will need to know that, but we're not doing it yet.
Okay.
That is forthcoming. I just want to get a handle on Poisson and negative binomial and get us situated into like a use case for this. Like when would you need this in your life? That's my goal.
Is it?
Yeah.
So if you go back really quickly,
Yes.
the 3.84, is that like a set number or is it different?
That is the critical value on the chi-square distribution for 1 degree of freedom, meaning adding one thing to the model at alpha of 0.05.
For a one-tailed distribution?
A chi-square is always is a square distribution. It only goes in one way.
So if you had a different p-value, you'd obviously have a different than 3.84, it'd be something different.
Yes, I believe it's alpha of 0.01 is like 6.635 or something, because I just talked about this in the class at 12:30.
Okay. I was gonna say, wow.
Yeah, no, numbers that I have to like type a lot, I tend to remember. But I can tell you for a chi-square for 2 degrees of freedom, a regular chi-square, the critical value is 5.99. For 3, it's 7.82, and for 4, it's 9.49. So, and no, you don't need to know this in your lives. The software will tell you. But back in the day, I had to look them up in tables, so I committed a few of them to memory. Okay.
So, sorry.
Oh, yeah, please do.
I'm gonna ask something really dumb. So, when we are looking at, we're comparing things to, distribution that can go both positive and negative, then we use p-values, and we wanna look at a two-tailed distribution, and we set alpha to 0.05, but it's looking for that 0.5 on both sides of the distribution.
Yeah, that's the thing. So if you picture like what k could possibly be, the use of a two-sided hypothesis test means we're testing the null hypothesis of 0 in the middle, and then it could go positive or it could go negative. The way that it's operationalized in here, k can't be negative. And that's actually that's the reason for the motivation of this other way of doing it called generalized Poisson. It's operationalized differently so that when k is 0, the likelihood is defined. Like in the way we're doing it, it doesn't work.
So then, what I'm trying to get straight is, so if I have a one-tailed distribution of any type, I would be looking not at a critical t-value, but a critical z-squared? No. What is chi-squared comparing?
Z-squared is chi-square.
Z-squared is chi-squared.
Yes,
So-
for 1 degree of freedom.
So there's a chi-squared value that a critical value that my number is being compared against
Mhm.
to determine if my result is likely within, like 0.5% of the data would be on the one side.
Right, and so like it doesn't make sense to allocate the other half of the 0.05 if it can't happen. And so this shows up in statistics in a bunch of different spots. It's known as like a boundary issue. Anytime you're testing a parameter that is 0 is the null hypothesis, but 0 is its boundary, a test that assumes that it could go either way can't be right. And there's different fixes for that. The one that is going to be used in this context is to say, well, if it wanted to go negative, like that can't happen. So we want to sort of eliminate that half of the distribution. When it is positive, that can happen, so we keep that. So in practice, it's a mixture of chi-squares with degrees of freedom of 0 for when the thing that didn't happen couldn't happen. And there is no such thing as a chi-square of 0. It's just 0. And so then what functionally ends up happening is because you just cut your p-value in half, it's like doing a one-tailed test. Because k can only be positive. It's more complex when you're adding more than one thing to the model, but it's the idea is that you're doing a one-tailed test for the things that can't go negative and a two-tailed test for the things that can. All sort of mixed together. You like that, Vladimir? He's nodding. You want to add anything to that?
No, it's hard when you must add more than one thing.
Yes,
Yes.
but that's not this class. that does show up in other places. Where this shows up in practice besides the K thing is when you add variances to a model. So in the multi-level modeling class, you have variances at level 2 and level 1. Those variances can't be negative. So a mixture chi-square is the proper way to test for those against null hypothesis of 0 as well. The reality, though, is that only in a very, very few set of cases would this matter. So if your likelihood ratio test result is somewhere between 2.7 and 3.8, that's when you would care about this. That's not going to happen very often. So ignoring this and all of it, then it just means you're being a little conservative if you ignore this problem.
So between 2.71 and
That is the point at which this distinction matters. If the result of your test, so if your model gets taller by more than 3.84, it would still be taller by this easier criterion 2. It's only when it's in between that would it matter what approach you use. Does that help?
I think it's a little over my head. I'll
Okay,
go
here-
back
all right.
and think about it more.
So this is the rightest way to do it in practice. Anytime that you're significant by this more stringent criterion, you're good. So doing it with ignoring the mixture aspect of it, just using a standard chi-square is a little bit conservative. That's the worst you can do, and I can live with that. You're just a little conservative, because you should be using this critical value instead. Am I making it better or worse?
It's not you, it's me.
No, this is sort of like an aside topic. My problem is that I want you guys to be like have shown everything on Earth, and then I don't have time to explain it all very well. That's my problem. But this will show up again in your coursework if you keep going. This idea of a mixture thing.
Any clusters?
In cluster, yeah, it shows up in multi-level modeling. It shows up in factor
Well, I'm
analysis.
thinking about this fall.
Yep, cluster data. Yep.
Yes. Okay.
Okay. Other questions?
I'm just gonna ask a really dumb question.
Now, don't say they're dumb. Questions are good. 3.84 on the chi-square distribution. So I know I put some in. Let's revisit this for a second with pictures, because this will help. Looking for my pictures, 1 second. This is lecture 2. Slide 22. So we're in this one right here. So the yellow line is the chi-square distribution if you added one thing to the model. And 3.84 right here is where 5% starts.
Oh, so slopes used. If we're thinking slopes used versus slopes left over.
That's more like F, but like this, so chi-square is used for many different things. In this context, it's used to judge the difference in -2 log likelihoods. Like, did it make the data taller enough? So if you add one thing to the model, all of this area right here, in terms of your test statistic result, is expected territory. After 3.84 is where you hit 5%.
My question is, what is X? What
X is the
scale?
value of the chi-square test statistic.
So it's just self-referential.
Yes. It's the difference
Not
in
the outcome.
-2 log likelihoods between nested models in this context.
The difference between.
Yes, X is the difference between -2 log likelihoods between nested models here. So like if you add two things, that's the green line. The critical value is 5.99, which is where 5% starts for the green distribution. Let me go down just a little bit of a rabbit hole to show you one more picture from my other class. You might recognize this actually. This is the longitudinal class where I had to take this and talk about it as well. Oh my God, it knew what I was doing. It pulled up the exact slide.
Wow.
Thank you, Google, or whatever artificial intelligence just did a solid for me. My goodness. No, I don't want takeaways. I'm the teacher. I know, this is creepy. So here's the chi-square picture. Do you see, let me zoom in a little bit if I can. Okay, do you see the dashed line and the not dashed line?
Mhm.
The dashed line is the chi-square if you have degrees of freedom 1, and the solid one is for the mixture. So 5% starts a little bit earlier for the mixture than it does for the non-mixture.
Cool, so-
How do we have mixture?
Where does
Is
that come
our
from?
degrees of freedom, like how many
Yes,
predictors are in your model?
so degrees of freedom in this context is how many things did you add? So we're talking in this context about adding a k stretchy factor to allow our distribution to have a little more skewness than the Poisson would want it to have. In previous examples, we added slopes, for instance, like proportional odds versus non-proportional odds. We added slopes. So if I added 3 slopes to the model, then that would be degrees of freedom 3. The 0, a chi-square distribution with degrees of freedom 0 is just a line at 0. It's not a distribution. It doesn't exist. 0 is anticipating what would have happened had k gone negative, but it's not allowed to. Can't happen. So the difference between these two lines, if your test result falls somewhere like there, that's when you would come to a different conclusion based on using this standard versus that one. 3.84 is more conservative, ignoring the mixture problem, and will only be wrong if your result falls somewhere in between these two.
Is it accurate to think that the degrees of freedom 0 is in a lot of with beta 0, which is like your base?
Not in this context.
Okay.
It's the mixture of when the other half of the distribution would have been used. So like for this one, here's 2. It's a difference of a critical value using a mixture of 1 and 2 degrees of freedom of 5.14 versus 5.99. So it's an even smaller differential.
I think the struggle for me is I think degrees of freedom should be count. But this makes it look like it's continuous. And I understand, like, if we have the stretchy factor.
So the x-axis is your test statistic, not your degrees of freedom. The shape of this thing depends on what your degrees of freedom are. So not this one, go back, this one. So the yellow and the blue and the greens and the purples all have different shapes because they're testing, they would be for different numbers of things added to your model. Slopes, k's, variances, like it doesn't matter what the thing is, but how many parameters.
So degrees of freedom is count, but the chi-squared statistic is continuous.
Degrees of freedom are integers for the number of parameters you've added to a model. Chi-square is continuous, but it stops at 0 because it's in a squared metric. That way positive and negatives don't cancel out.
Because how can it be between 0 and 1 if it's an integer?
Degrees of freedom are integers, not chi-squares. Count outcomes are integers, but we're not talking about that. Vladimir, please help me. I'm dying here.
For example, in homework, when Lisa asked about test statistics,
Yes.
what we introduce in the boxes is what you have, for example, from the livelihood ratio test. The number that reflects the difference in -2 of livelihood between models. That's the test statistic. That's a continuous thing. It can be any positive number. And that's what that's labeled as test statistic.
Yeah,
Which
and
in
that's this
context
axis
is
right
a
here.
chi-square. Yes. So maybe that can help.
I guess I'm confused because if it says chi-squared for a mixture of degrees of freedom 0 and degrees of freedom 1, how can it be a mixture?
Oh. Can I help with that too? Because
Yes, please.
I had similar questions when I learned this. But in this and in other class, we know that mixture means that we are mixing things. We are combining things. So here, what we have underlined here is 2 distributions. One distribution, as Lisa said, is when your variance is negative, something that cannot happen. So that now is being represented by this idea of a chi-square distribution with degrees of freedom equal 0.
Because it can't happen.
Yes, so that's one thing. The other part is the chi-square distribution with degrees of freedom equal 1 because you are adding one thing. Let's say random intercept or random slope.
The k stretchy factor is the
In
context
this case,
for here.
Yes, exactly. So when you combine both things to test your test statistic, that's why it's named mixture. So because it's both things at the same time.
You
Yep.
guys have been so kind. I don't understand degrees of freedom 0, but maybe it's not, now might not be the time.
Yeah, it's a silly
Office
thing.
hours.
It's a silly thing. It's trying to anticipate what the shape should look like, and it can't be two-sided if something can't go negative. So we're solving that discrepancy.
I think, I'll come to office hours.
Okay. Okay, fair enough. All right. Now numbers?
Sure.
Sure. Can I tell you a story behind the numbers?
Okay.
This entire analysis as described, the paper that this is related to is right here. It's in your download folder.
Gee, did you have anything to do with this paper?
I might have. This might have been one of the graduate students in the class the first time I taught it. This might have been her advisor, and this might have been me. So here's where the story starts, okay? I had consulting office hours. This is at the University of Nebraska in the psych department. Let me get to the picture here. And that student came to my office, showed me this piece of output. It was an SPSS. Now, how would you characterize this distribution?
Looks exponential.
It's highly skewed, right? It does
Oh,
not
yeah.
look symmetric, right?
If and how many?
Yeah.
And there's mostly in the if, not the how many.
Yeah, it kind of looks like there's a whole bunch of people who have a 0 and a mixture distribution, right? Because you have a mixture of 0 people and not 0 people.
Ding, ding, ding.
Yeah, it shows up in a lot of places. And so we can agree that whatever this is, it ain't normal, right? It's not symmetric, it's clearly bounded at 0, and this is a count of the number of mean things that was said during an experiment when people were deliberately manipulated to try to piss them off. Okay, that's where the story was. This is a clinical psychologist who studied interpartner violence and those kinds of things. These are college students. The question that she came to my office hours with was, how do I transform this to make it more normal? Any ideas?
Well,
I could do a log transformation or a square root transformation that would reel in these people out here, make it less skewed, but there's nothing I can do that takes 45% of her sample who's a 0 and somehow spread them out. It's not possible. So then I asked her, why do they need to be normal? Like, why is that a thing? And it turns out that she had planned this study. Back to the story, the origin of the story here, where she had measured whether or not the students had a history of interpartner violence, basically being mean to each other in various ways, and they were randomly assigned to 3 different experimental conditions, where they were given strategies with which to moderate their responses to these manipulations in terms of trying to make them mad. One group was told, do whatever, that's their control group. One group was given cognitive reappraisal strategies, and you can read about this in the paper if you're curious. And another group was told to just suppress it. Just stuff it all back inside, don't express yourself, it'll be fine. Spoiler alert, suppression is not good. Right, we do have you're counseling, right? Both of you guys? How'd I do?
No, it's accurate.
Accurate? Do you want to talk about cognitive reappraisal?
It's like a CBT. It's where you sort of restructure your cognition to be more rational.
Like, think about it from another perspective that might make you
Well,
feel
'cause
better?
In many cases, when there's intimate partner violence, one or both of the partners are either in denial or there's rationalizations that are unhelpful.
Mm-hmm. Yep. So no one was getting hurt during the study, by the way. This was just people were manipulated to get grumpy, and then they were asked to use these strategies, and they thought that people who had a history of violence would respond differently to these manipulations. So she's hypothesizing essentially some interaction terms. So the way that they approach this is a fairly standard, like, factorial analysis of variance. This would be like a 2x3 ANOVA. And that was why she thought that her outcome had to be normal, because how else are you going to do the ANOVA? And so I was like, well, why don't you do your ANOVA with the count distribution instead? And she's like, what's that? So I asked if I could borrow her data. I made this example. It was like one of the first ones I ever made. I've tweaked it quite a bit since then, but then I helped her publish this, and this was her master's thesis
fair.
that became this paper.
Cool.
Now, would you like to know why she was concerned about normality? This is my best guess. I'm going to give away the story here. The p-value for the interaction that would confirm her hypothesis was 0.0579 if she uses a normal distribution. I'm pretty sure that was what brought her in. It's like, is there anything I can do to, like,
Good,
fix
bring it
this? Turns out it is going to get fixed. The p-value is going to be decidedly significant once you fit the right distribution. Because the distribution you use is how you build the standard errors, which is how you get your p-values. So she was assuming constant variance across all levels of her outcome, which is not going to be the case. When you have a picture that looks like this, there's going to be a lot less variance on this side of the distribution than that side. It needs to be non-constant. So I taught her how to do an ANOVA as a count model, and now I'm going to teach y'all. So it's a real story, and that's why the data aren't in your file. Now let's first talk about hypotheses. These are the research questions as stated in the paper. Let's practice mapping them onto what are we going to look at. So IPA, by the way, reviewer 3 insisted that we had to call it intimate partner aggression and not violence because of the way we measured it, and so we were like, fine. But IPV and IPA are the same. We'll change that. So IPV perpetrators will express more aggressive verbalizations, that means numbers of mean things they said, during anger arousal, meaning after we deliberately piss them off, across emotional regulation conditions. How do I operationalize that idea as some kind of fixed slope or multiple slopes that will answer the question? What am I talking about? So these questions are irrespective of what kind of distribution we're using. I'm just trying to build a linear predictor. So IPV perpetrators will express more aggressive verbalizations during this task across conditions.
You can only count.
Yeah, it sounds to me like a main effect. We're saying that the yes people are going to have higher outcomes than the no people across conditions. That's a main effect. Compared with individuals instructed to use cognitive reappraisal, individuals using expressive suppression will experience more aggressive verbalizations during anger arousal. It's a lot of syllables. What does that sound like? Yeah, it sounds like a main effect that way, right, for both of them? That people who are doing suppression are going to have higher outcomes than people who are doing this one, and probably higher than the control group as well. So we know at a minimum, we need a main effect of IPV to answer this question. We know that we need a main effect of none versus cognitive reappraisal versus suppression to answer that question, number 2. Now, number 3 is very long, but here's your key. Will interact. So people who are perpetrators within these 2 conditions will express more anger compared to these people, whereas no differences will emerge in this one. So there'll be a bigger difference in IPV here than here. A difference of a difference. That's an interaction term. Now, question for you. How many slopes does it take to get my main effect of IPV into the model, if that's a binary predictor? If I have IPV as a binary predictor, how many slopes does it need to express its main effect? Just 1. If I have condition as 3 categories, how many slopes do I need to express its main effect? 3. Yeah, 2. If I want the interaction term, how many of those do I need?
2 per interaction that you're working with, yes?
I would need 2 in total, because I have, basically if I want the effects of condition to vary by IPV, and condition took 2 slopes, the interaction will be 2 slopes as well. So in this example, the model for the means, the linear predictor, is not going to change. It's going to have an intercept, it's going to have a main effect of IPV, it's going to have 2 main effect slopes for condition, and then 2 interactions. How many is that? Intercept, main effect of IPV, 2 slopes for condition, and then 2 more for the interaction?
Smallest perfect number.
Yeah. 6. How many squares do I have here? 6. Is that a coincidence?
No.
No. So this model is going to perfectly recreate these 6 means. The slopes are going to piece them apart in various ways. So you don't have to express things as main effects and interactions if something else would be more convenient. An equivalent interpretable model could be, I have 6 means, prove me wrong. And then I could use LinComs and GLHTs to ask for differences among them. So I've got 6 means, 6 fixed effects are going to perfectly recreate these means. A lot of words about the packages I'm using and why. First thing I got to do is make my predictors. So my original variable is called ERCON for ER condition. It is 1, 2, or 3. I need to create 2 new variables for that. Why is that green? There we go. And I'm doing that by starting them off as blank. That means empty. And then N versus C, that means none versus cognitive. N versus S is none versus suppression. So I'm setting up the control group as the reference, and then the slopes are going to tell me about each other group relative to that. So the control group is group 1. They get 0s in both spots. The cognitive reappraisal group gets a 1 in the first one and a 0 in the second. And the suppression group gets a 1 in the second one. So this is standard indicator dummy coding against a common reference group. There's some labels, filtering to make sure we have complete data. In R, it's the same idea, but just with a little bit different code. So starting out by making blank variables as NA, and then systematically recoding them. For group 1, they're both 0. For group 2, the first one's 1. For group 3, the second one's 1. And then filtering. Then I made some pictures. So in Stata, I'm using hist for histogram, and then saving the pictures. These are in your download file. Actually, I think that part needs to be fixed. And then in R, I'm using hist as well. Here, I'm going to give away the story. Here's where we're going to end up. So here are my 6 squares. I have different numbers of people in each of the squares because I can randomly assign which condition they're going to see, but I can't randomly assign people to be violent or not. IRB might have a problem with that. So it looks like the yes conditions are smaller. Good. Violence is bad, right? Usually. The maximum count varies quite considerably across these conditions. Someone said up to 24 mean things. The maximum in this cell is 1. This is like the definition of heterogeneity of variance right here. If you look at the differences in the standard deviations across these cells, one common variance is not going to describe these data very well at all. One strategy that we could use is to make 6. There are options within this family of models where you can allow the predictors to dictate how much variance is in there. Basically a separate variance for each combination. That's one type of choice. I'm going to show you something that's a little different using different distributions instead. So look at the green and yellow columns. Those are the predicted means of our outcome. Do you see anything that looks in common across those? They're all the same. So the model, regardless of whether we're using a link or not, is going to get the right expected count back to us. That's what these are. The means of these variables by cell, these are expected counts. So in the raw data, the normal distribution is going to give us back because we have 6 parameters to capture the 6 means. Same is true in Poisson. Same is going to be true in negative binomial. But what about the standard errors in the pink and white? Those don't agree. So the standard error of the mean differs in just the raw data because of the sample size, but it's assuming that there's like a common variance for normal distribution. So if you look at the spread of these standard errors of the means, they're a lot closer together under normal, they're a lot smaller under Poisson, and they're a lot more variable under negative binomial. So this difference in what the standard error of these means, that's going to translate into different standard errors for your slopes, which translates into different p-values for your conclusions. So the story here is all about distribution. we know the linear predictor is right because there's only 6 possible means and our model is going to get them back regardless of what we choose. Because we spent all 6 degrees of freedom in terms of number of data points to do it. Here are the by cell distributions. So quite a bit of variability across these cells. Not a one of them really looks normal to me though. So my student who brought me this picture, in addition to the fact that I can't turn this pile of zeros into anything other than what it is, let me ask you guys the question. Does your outcome have to be normal to use a standard regression model?
Standard regression?
Mm-hmm. What's the difference? Outcome or residuals? So what's the difference between an outcome and a residual? Yes. Tim, you were going to say?
So the residual is the distance between the actual and the predicted.
Yep, how wrong you are. That's what your residual is. The assumption behind standard general linear models about normality is not the original outcome. It's the residuals. So this doesn't even have to be normal for her ANOVA to have been correct. However, what this plot is showing is because this is by cell, these are the residuals. This is after controlling for which condition you're in and what kind of IPV person you are. So not only are these not normal, they're very different in shape. So non-constant, not normal. If only there was a way we could solve this. So think about what the mean and the variance means being the same in these things. If the blue line says the mean is 5 and the variance is 5, what if a person under this distribution were predicted to have a mean of 10? What would the variance around the 10 be? 10. What if a person were predicted to have a mean of 15? What would the variance be? 15. Not constant. It's tied to the mean. So Poisson solves the problem that the data are likely skewed, like this, and that the variance should grow along with the predicted count. All in one step.
So just to check out for clarity, Poisson is it only addressing the distribution, or is it also creating these subcategories that you're creating here, which I'm not complaining about?
It is addressing the distribution. What do you mean by subcategories?
It seems like a piece of the reason why the distributions are changing is because you're now creating these different models, and so now you're looking at how people's placement in the different groups has changed the distribution overall.
I would say I think it's the other way around. What we're looking for is a distribution that would capture these possibilities. So each of these cells has a different predicted mean, which means each of these cells is going to have a different predicted variance. The fact that these values are piled up at 0 and then spread out, the log link is going to fix that problem to make sure that our predicted counts stay above 0 where they belong.
So Poisson predicts that the model will be more accurate for lower ranges,
Mm-hmm.
and it will be less accurate at higher ranges.
That is correct. If you have a really high count, there's more room to be wrong about it. If you have a predicted count of 1, there's less room to be wrong. You can't go below 0. There is, let me get out another slide. This is, no, I think it's that one. I think it's lecture 1 I want. It's like a greatest hits collection. Is it this one? This is Legos. Yep, pictures in here. This is what I wanted. This is slide 18 of lecture 0. This is what we're talking about. As the predicted count increases, the variability around it increases too. So this is heterogeneity of variance that we're showing here, this fan size, versus homogeneity where the dots are equally spread out no matter where you are on the line. That corresponds to an assumption of constant variance in the normal distribution, there is only one variance, so it has to be assumed constant. In Poisson, the variance is a function of the mean, and as the mean changes, the variance changes. Negative binomial adds its tweak to that, and it says as the mean changes, the variance changes, but even more. It grows quadratically as a function of the mean. Not that one. I've got too many things open at this point. There we go. Here we go. There's the formula. So the variance in the negative binomial is going to be the mean plus the stretchy factor times the mean squared. So it allows the variance to grow even more than the mean, but they're still yoked together. So we estimate a k, but we don't estimate a variance. We estimate a mean and a k. Build the mean out of the fixed x. All right. So the story has a happy ending. We'll get to see more of the story on Thursday, but the happy ending is that she got to publish her paper.
Do you have pictures after you fit a different curve?
I did do, for the normal, I have a picture of that, I think, but I didn't do the others. Yeah. So like this is SAS output that does diagnostics and stuff. So here are the distributions of the residuals combined across the 6 cells, and then here is the fit to a normal. These dots are supposed to be on the line. It's not. And you see there's a pile here still. Like these are the people that are 0. So note that the residual distribution looks very different than the one we started with. Remember we had a pile of people at 0 and now they're gone. Because the model explained them.
So it's predicting 0 outcomes, but that's okay because if you transform them back to the outcome, because this is in the log.
This is in, no, this is pretending that the count is normal. And this is the fit of a normal distribution to the residuals.
So this is bad.
It is bad, but the point that I'm trying to make is that, remember how we had a big pile of zeros at the front? It's gone. Because the model predicted why a lot of the people were zeros. It's because they were in this condition and they're not violent. So I'm trying to highlight the difference between a residual and an outcome. Some of the zero inflation, the piling of zeros, can be accounted for by the linear predictor, meaning it's not going to be a problem anymore. So we're going to do an ANOVA on count data, and it's going to be fine. How's that? But it's 3:14, so we're not doing that today. All right, other questions as we wrap up on this garbage day?
Is there a class in here after this one? I don't think so.
I don't think there's a class in here afterwards, no.
Yay. I have to hold a meeting with the person at 3:30.
Okay.
I'll
All
have
right.
to find a new spot.
Then keep working on your homework. If you haven't finished it already, let us know if you need help, and I hope to see you all Thursday. Thank you. Bye for now.